feel like me sitting here is actually not going to work because I can't see you guys. I'm going to move to a new spot. I keep trying out these new classroom orientations. Okay, how about this? That's not bad. Okay, let's do some review of what we covered. We're good. Let's do some review of what we talked about before we had our Easter break. Okay, so we had 5 topics. Why don't we work backwards, actually, rather than forwards? So I'm actually going to start at the end, the thing we talked about last, which was the photoelectric effect. Okay. Maybe the best way for me to start with the photoelectric effect is to imagine a scenario where you're heating up like a horseshoe in the furnace, the fire, the forge that you want to pound it into a new shape, right? And it's a black horseshoe. And as you put it into the flames, it starts to glow red or yellow. You guys have envisioned and seen this sort of thing before, right? I mean, when we talk about how light happens, the reason why we perceive colors and we perceive things is that light bounces off of said object. Then almost all of the wavelengths of visible light get absorbed except for the color that gets reflected. That color then gets reflected to our eyes, and we're then able to perceive that color, right? So when I see a blue shirt or a red shirt, it's because that's the only wavelength of light that wasn't absorbed by the object. What happens to black objects then? They more or less absorb almost the entire color spectrum, right? And that's what makes it so that you don't see anything. Miss McCarthy, before she left when she was here for PS3, she showed you that little YouTube video clip of Vanta Black. You guys remember this one at all? Where like it's so black that you can't even see the detailed edges of it. It was that light absorbent. Okay. Now back to my horseshoe example. When it comes to the horseshoe, classical physics predicted that what should happen is that a black object should not only be able to absorb all frequencies. You know, this black object here is basically absorbing all frequencies of light. You get a little bit of shimmer and sheen off of it, so there's a little bit that gets reflected, right? But most isn't, right? But a black body object should not only be able to absorb, but it should also be able to emit those colors. So again, back to the horseshoe. The horseshoe is a black object, right? As we heat it, if we were to heat it in the dark, it would still glow then red, then yellow, then white hot kind of colors, right? Well, why is it doing that? It's clearly not reflecting those colors. Because what's happening is it's actually emitting its own source of light. Now, here's where this ultraviolet catastrophe came in. According to the way classical physics would occur, what should happen first is as those molecules heat up and they start vibrating, they move faster and faster and faster as they get hotter and hotter, it should emit visible light. It should start with, say, red, and then move its way through yellow, and then according to color theory, as these colors blur together, eventually it might emit white light, which is, maybe you've heard the phrase like it's white hot, right? That's because as it heats up, it keeps increasing in intensity. Well, here's what you'd expect. As we keep heating it hotter and hotter, it should then eventually create ultraviolet, then X-rays, then cosmic rays. Well, that would be horrible, because that means that if we were to heat a fire hot enough, we would all die due to radiation poisoning. You know what I'm saying? And so that's where the ultraviolet catastrophe came in. And it actually wasn't a catastrophe whatsoever. It actually is very fortunate that once we get to ultraviolet, it just seems to stop. But here's the problem, is classical physics couldn't explain this. So a new theory basically came up, which was Max Planck's idea of, well, what if energy isn't able to be in any single amount, right? Like imagine that you have, what's a good example here? Time. Time, maybe you've heard the words discrete versus continuous. We think time is continuous because, I mean, let's say that we talk about a unit of time like, say, a year. Can we have half a year? Sure, why not? Could you have half a second? Could you keep cutting that second into smaller and smaller and smaller chunks? As far as we know, we seem to think we should be able to. There are a lot of things, though, that are discrete. Like, for example, a shoe size is a good example. I can go to the store and I can buy size 11 shoes. I can buy size 12 shoes. I cannot buy size 11.95327 shoes. It's just not possible. You guys know those words, discrete, continuous? So Planck revolutionized the science by saying, well, what if energy can only come in individual packets? And what that means then is, you know how the frequency is going to affect the energy that occurs? Well, if you keep shortening the wavelengths smaller and smaller, you keep shoving them in there, what they basically suggested is maybe there's a maximum. Maybe you cannot shove these frequencies in smaller and smaller and smaller. Maybe there is actually a limit. And maybe that limit helps explain that ultraviolet catastrophe issue as to why all of a sudden certain things just stop emitting. Now, I don't understand the equations he used And to be honest, it's more than fair if you guys don't either, because it's just, I mean, this is Max Planck. I mean, this is one of the smartest guys of our, well, not our generation, but one of the smartest scientists ever. So please don't freak out if you're like, I don't get the math behind it, because like, I'm sure about 12 people in the world do. You know what I'm saying? So, but so long as you can accept the premise then that energy is quantized, it changes everything. Because now the basic idea is, well, now if energy is actually a particle, a photon, it now explains this photoelectric effect about how if a light ray comes in and hits a metal, it can cause an electron to get shot out. And we utilize that nowadays like crazy in photovoltaic cells, which is a fancy word for, it's a photovoltaic cell. Like a solar panel, yeah, essentially, right? I mean, especially in 2017, we're talking about green energy and new forms of electricity, right? Trying to get off of fossil fuels. The idea of being able to harness energy from the sun and not combust fossil fuels. The idea of basically being able to have a certain wavelength of light and get the electron out. If we can harness that power, that's brilliant, isn't it? So, anyways, let me go back to my notes here a little bit. It basically led to, where's a good picture here? Yeah, here's a good picture. This concept then is as this photon, this packet of energy comes in and hits the metal, it could, keyword here, could knock out an electron. Okay. But we have to consider conservation of energy. It's going to take some work to knock out that electron. That electron isn't just going to all of a sudden be like, okay, bye-bye, right? Like it needs to actually do a little bit of work to force it out, right? And that's where this formula came from here. This is known as the work function, is Planck's constant times by the threshold frequency. There needs to be a minimum amount of frequency for it to knock the electron out, which is why radio waves and microwaves and infrared light and most red and yellow light doesn't do this. But your blue, your green, your ultraviolet, hey, there's that ultraviolet kind of borderline area coming in again. Those portions of light actually are able to knock out electrons. Does that make sense? And we saw that in the little simulator I did. Let's just do it one more time just to be thorough here. Where's that simulator? There it is. So here's the simulator. If we were to turn on the lamp, all of a sudden, hey, look, the electrons are getting hit from the side of metal right here, and they're able to go across the vacuum tube and basically cause a current to exist. But that's only because the wavelength is basically on the threshold of that ultraviolet. If I were to back this up to red light's not strong enough, I guess. Strong's not the right word, though, because I think strong would refer to how much intensity we have. The intensity does nothing, right? If I turn the light just barely on or I turn it on full blast, it doesn't matter. What really matters is that I change the frequency, because the frequency changes the energy. You guys all good with that concept? So, anyways, I mean, this is a revolutionary idea. If I had to somehow arbitrarily rank the most important accomplishments in physics, this has got to be on anyone's top 5 list. Like, this was huge. Right? At the time, physicists believed that they had learned everything that they needed to know about physics. I don't remember whether I told you this story or whether Kelsey did, but you guys ever heard the name Lord Kelvin? He gave a speech in about the year 1900, and he basically said that physics, we know everything in physics. We're good to go. We've got it all figured out. Was basically his concept here. And I mean, this was a pretty important figure, Lord Kelvin, in terms of science, and they couldn't have been more wrong. I read a story somewhere that says that Max Planck, his parents wanted him to go be a musician. Did I tell you this one? They wanted him to be a musician because at the time, people figured that physics, there was nothing more to learn in physics. We were done, and so physics would be a dead-end job. You would be poor being a physicist, which is funny because nowadays, if your parents were to push you into music or physics, they'd probably say, don't be a musician. You're not going to make any money doing music. Go be a physicist, right? Complete opposite. And yet, anyways. Okay, this is a really important graph. So much so that I made you guys do this in your lab. Because this key x-intercept right here then is the threshold frequency for which it requires before you can actually knock electrons off of the metal. If we were to continue this graph right down all the way to the bottom here, do you guys remember what the y-intercept would be known as? What was that? Good, that's right. This would be the work function. Which is just a fancy way of saying This is the amount of work you need to at least have from energy coming in from the photons of light or whatever to knock the electron out. If you don't have at least that amount of energy, then it's not going to work. I mean, work functions then, actually I should take that back. Work functions really depend on the metal though, right? Because sodium has a different work function than calcium, which has a different work function than zinc. So you may have to look that up in a table. Where's the table? There we go. Here's a table. That's the minimum amount of energy required by the metal to bump the electrons out. Sound good? Okay, one more thing and then I'll keep working backwards in our notes. Someone else brilliant, I think it was Millikan. It was Millikan with the photoelectric effect. He was smart enough to figure out, well, let's try to figure out just how much energy these things have. And so he used something called a stopping voltage. And I think this was something that screwed many of you up on your quiz, is that you had to kind of write yourself your own equation involving stopping voltages or involving like E equals HF minus W. But the basic idea is you turn the battery on. And if he reverses a battery, you see how the electrons are trying to leave, but they're not able to? That's due to the stopping voltage. And by manipulating some mathematical equations, more or less involving conservation of energy, here's a good one. The energy of the photon is the energy of the electron. HF equals work function plus kinetic energy. He was able to calculate just how much kinetic energy you'd be able to knock these electrons off with. But you had to use, here it is, this formula here to find the stopping voltage. This was how much voltage you needed to turn on to prevent the electrons from flying away. Q is the charge of the electron. That then would help you calculate how much kinetic energy these electrons were trying to leave with. So all of these things kind of piece together like that. Does that make sense? I don't want to literally go through the whole year again. But so that was topic 5, more or less in a 10-minute nutshell. Okay, working backwards. Topic 4 then. All about the idea of light, EMR, anything in that spectrum is a wave. And one of the reasons why we know it's a wave is due to Young's double slit experiment. Here's a good picture of it. In Young's double slit experiment, he sent a wave through this hole and this hole. And you would expect on the following screen over here to literally get 2 lines. That's what you'd expect with classical mechanics. You'd think, well, whatever comes through here would go right there, and whatever goes through here would come right here. And you might expect maybe there's a little bit of a range, because like maybe it could like tilt a little bit to the sides of the holes. That's not at all what happened though. They got this pattern here, where it was like a dark spot and then a light, and then dark and then light, and then dark and then light, and then dark and then light, repeating over and over again. The reason why is that light is a wave, and as a wave, right here and here and here and here, all of these spots here, light is constructively interfering with itself, causing there to be a positive interference pattern. Whereas in other spots, like say here and here and here and here, that would be destructive interference, where the crest of one wave and the bottom of the other wave are actually canceling each other out. And so this was actually another revolutionary concept of how, well, maybe light isn't actually a particle. But wait, it is a particle. No, but wait, it's a wave. That's actually tomorrow's topic, is to revisit the idea of how light apparently can be both a particle and a wave. What I really need you guys to be able to do from this lesson is know how to use the 2 formulas. And these are the 2 formulas here. They're fairly straightforward. You get 4 out of 5 variables you solve for the 5th one. So, does that sound good? Okay. Previous to that, working backwards, we would have talked about reflection and refraction. Refraction basically involved this formula here. Where is it? They both involve the same formula. Come on. There's a good one. Here it is. Snell's law. Snell's law involves the formula for either angles, indexes of refraction, wavelengths, or velocities. You guys remember how to use this one? Okay. And then with reflection, both of these things can kind of involve mirrors or lenses, which would involve these formulas here, the focal length and the magnification formulas. And then going back, the first day we would have then just introduced you to the concept of EMR. Yogurt, cheese, muffins, bananas, apples. Okay, so that quick, yeah, that wasn't quick, that was half an hour. But that review of what we've gotten to takes us up to the year, I think it was 1923. Okay, and so we've gotten past Max Planck figuring this out. It was basically the turn of the century. Okay? And these theories here then cause scientists, I'm just going to read off my notes here, to really re-examine their basic ideas of how EMR worked. Okay? Look, they knew that it acted as a wave, but it also looked like it was a particle as well. And so this was more or less based on Einstein's work. But physicists predicted that a photon should have momentum. But I need to pause for a second here. A photon is energy. A photon would be like a packet of light. And what they predicted is that if it can act like a particle, it should have other properties of particles or other properties of matter. Right? If I were to throw something here, it has energy. That makes sense. We knew that light was energy as it was anyways. That didn't really change much. But they figured if it can act with energy, why shouldn't it be able to also have momentum? What's the formula for momentum? Mass times velocity. Well, I feel like we should be able to figure out the velocity of these things because, well, what's the velocity of all EMR? Speed of light. There we go. That one's straightforward. If it's supposed to be able to have a momentum, though, then that would actually mean that light particles actually have a mass, which is just like, hang on a sec here. Light has mass to it? You're telling me that that light that's coming and shining off of me actually weighs something? But that's kind of what it would imply, is that these packets of light have momentum. And so here's how the work was done. It was actually a lot of formulas put together. I'm going to show you this on the next slide, but here was a formula derived to help you calculate momentum. Okay? It's momentum is equal to Planck's constant divided by the wavelength, or you could also do Planck's constant times by frequency over speed of light. And these are two formulas that I believe are on your formula sheet. What I want to do on the next slide is show you how they calculated this using like multiple formulas. So here's your base formula. Momentum is mass times velocity. That's what we've learned previously. Well, now the assumption is, well, what if light has a mass? Well, okay, that's a little bit more challenging to figure out because how in the world would we ever find the mass of light? Could I just shine a light on a scale? No, it's going to be way too small for that. Now, that being said, I've already given you guys previously a chance to hear light. Remember how I took the camera and I shone it on the symbol? You could hear it hit the symbol? I mean, that would certainly seem to indicate that there was definitely a collision that took place. But I don't think experimentally we're going to find a way to do that with math. This is brilliant. You guys have seen this equation before in your life, right? E equals mc squared. That's probably another one of those like top 5 discoveries. That was Einstein. So Einstein rearranges his E equals mc squared formula to try to solve the mass conundrum and say, well, then the mass would be equivalent to the amount of energy you have divided by the speed of light, and he plugged that guy in there. So momentum is now energy over the speed of light squared times velocity. But then we said, well, hang on a sec here. Is the velocity of these particles, is it not also traveling the speed of light? So really, isn't this also c? Isn't the velocity of the speed of light? Which really means that you can cancel this and this one, and it leaves you with a formula here of momentum being energy over speed of light. But then he takes one more formula and says, well, according to Planck, energy was Planck's constant times frequency. So he basically takes the HF and plugs into the place of the E, and now we have this new formula. Momentum is Planck's constant times the frequency divided by the speed of light. Or, with another little trick here, you can also rearrange the frequency, because frequency, speed of light, and wavelength are all related to each other. Or you can also get this formula. So the math was actually really easy. Right? By taking 3 or 4 formulas here and kind of plugging them into each other, they solved the conundrum of how the heck you deal with mass. And now we have a formula that should get us a momentum of a particle. Sounds good. How do we prove this? Well, that's a little more challenging. So this is where Compton comes in. 1923, he has this, I don't know, brilliant idea of, hey, let's shoot X-rays at things. You guys ever heard of Madame Curie? Yeah. What was she famous for? What was that? Well, she was famous for many different things, but probably her death is one of the most things she's known for because she died from radium poisoning. Because back in the 1920s, they had no idea what this stuff did, right? And so as scientists, they were working with like X-rays without lead vests, or they were working with radium without realizing that it was giving off gamma radiation, right? They didn't have proper protection at the time, so Unfortunately, she's actually known for dying due to, her discoveries, which were groundbreaking, but it cost her her life. Anyways, 1923, Compton's doing probably some similar stuff. He's messing around with X-rays, which nowadays we would not play around with so flippantly, right? You guys go to the dentist, right? They put the little thing in your cheek there, and then they go hide around the corner, right? You don't mess around with X-rays. Enough X-ray exposure causes problems. Anyways, his idea was, let's shoot some X-rays into graphite. Do you guys know what graphite is? Yeah, basically. What's it made out of? Carbon. It's basically carbon. Okay. So she shoots X-rays into a piece of carbon. Okay. And what ends up happening is, as the X-rays hit the carbon, they actually become a smaller wavelength. This is what you'd expect. You'd expect, if light was a wave, you'd expect the X-rays to come out the side with smaller wavelengths because they're, getting compressed somehow. As they hit this material here, they're going to get compressed. That's what they'd expected. But Compton actually discovered something completely different. This is what actually occurred. He shoots his X-rays in, and rather than being compressed because they hit something, right? I mean, just think collision theory, right? I mean, if I were a football player and I were to hit a brick wall, I would get squished in a little bit, right? But this is what actually happens instead. His longer X-rays, or his X-rays here, actually become longer. They don't become shorter after they hit the material. They become longer, which seems backwards. Because, again, wouldn't you expect that if something hits, it would compress? It doesn't compress, it gets longer. But more importantly, it also shoots off an electron to the side. Hey, Tom, are you looking at me here? Sorry, say that again? Okay. Is everything okay on your end, Tom? Like, can you hear us still?
Yeah, the computer's just bugged out. It's trying to restart its
Okay. Should I just wait for a little bit here, or do you mind if I keep kind of talking over top of you?
I think I fixed it.
Okay.
I think we're good.
Okay. Okay, so here's what he discovers. Rather than the wavelengths getting compressed, which all logic would dictate that as the waves come in, you'd think they would get shorter, right? They actually become lengthened. But now that we think about this using quantum theory, that actually makes sense because the shorter the wavelength, the higher the frequency. Start again here. The shorter the wavelength, the higher the frequency. The higher the frequency, the more energy they have. Does that make sense? So right here, I have a wavelength with, let's say, a fairly high energy. And as these waves hit this graphite, they actually become longer. Well, if they have a longer wavelength, what does that mean about the frequency? Frequency is decreased. Well, if the frequency is decreased, so has the energy. The energy must have gone down. They've lost some energy. So X-rays with a high frequency are still X-rays. They're just lower frequency. Well, we can't just randomly lose energy. That doesn't make sense. Well, where does that energy go? Well, actually, it helps perfectly explain why electrons were getting spit out at a bit of an angle. And so we were actually able to do some momentum issues with this. So using conservation of energy, conservation of momentum, and the idea of photon theories, Compton was able to explain all these, and so we call this thing the Compton Effect. So if you ever do something really groundbreaking in science, you name it after yourself. So, or you can name it after your favorite high school science teacher. Just saying. Anyways, based on this, he was actually able to predict how much change in wavelength was expected. Because there was a certain distance right here of wavelength, and he was actually able to predict how much he thought the wavelength was going to change. And so he came up with this formula, which is right here we go. there's the formula which we'll get to. I'll flip back in a second here. But he was actually able to experimentally visualize this same thing that he was predicting. Sorry, I jumped around there. So here's another picture of the example. In comes a high energy wave. Now, Compton used X-rays. I found this photo of gamma rays. Same difference. So gamma rays, see how they're very short, compressed wavelengths? Now, they are so short that these wavelengths penetrate all matter. They would go right through the table, right through the cinder blocks, right through your body. But they're so small that as they miss the nucleus even, they might hit an electron. And as they hit the electron gets bounced this direction here, but this wave does not keep going with quite the same energy that it began with. It loses a little bit of energy in order to knock the electron that way, right? And can you guys see how these waves right here are just slightly pulled out a little bit? If it was like a slinky, the slinky's been extended just a slight little bit. Right? There's been a change in energy from here to here as the electron gets ejected. So then if EMR acts as a particle, then it must have momentum. So what we can do is we can do calculations on this, just like in the first unit, which you're not going to like. Because, remember these whole break it up into the X and Y conventions? This is the third possible spot in physics where they're going to give you a two-dimensional problem. So you could get one in momentum. We also did these in the forces and fields unit, where you were trying to calculate like the electrostatic force between multiple particles. This is the third spot this could occur. Where you might have to figure out momentum as a conservation momentum sort of thing. Where you'd have to break it up into the Y component, the Y component, the X component, the X component, that X component there. Does that make sense? So the good news is, if you need to calculate a momentum, if it's an electron, well, the electron, you can just use P equals mv to find its momentum. Because an electron, we actually know its mass. Its mass is 9.11 to the minus 31. So this electron right here, we know its mass, and we hopefully can either tell its velocity or solve for its velocity. So mass times velocity is how we're going to calculate the recoil of the electron. For the incident and scattered photon of light, you'd use h over wavelength in both of these cases. Now, h is not going to change. It's a constant. What's happening to your wavelength from 1 to 2? Your wavelength should increase, because an increased wavelength means a decreased frequency, means a decreased energy, which makes sense because this thing should lose some energy. Hopefully you can follow that train of thought. So let's try some examples in a second here. There's also one more formula you need to figure out here. If you want to figure out that change in wavelength, if you can tell me how much the wavelength has changed, then he was able to actually figure out the angle at which it's scattered. And this was the formula, and I have no idea how he came up with this, so please don't freak out over that. But it's h over mc 1 minus cosine theta, and that would actually get you the angle at which the theta at which the electron was scattered. So let's try an example. I just have one. It's fairly straightforward. Let's try drawing it first here. We have an X-ray, and I told you its wavelength when we started. I'm just going to draw a bit of a picture here. Here is a wave coming in, and it gets shot at a piece of graphite. On the other side, the X-ray is observed to have scattered at an angle of 15 degrees. So why don't I make that go downwards here? And I'm going to draw these a little bit further apart here because I recognize that they're losing energy. And if it were to have gone straight through, this angle here is now 15 degrees. Okay, well, this thing's not just all of a sudden making a 15-degree turn on its own. What else has got to happen? Yeah, it's going to shoot an electron out. So why don't I have the electron, I'm going to use a new color here. Let's have an electron get shot up that way. So this is essentially the curling peel shot question. Remember that from our first unit? Here's the stone is just sitting here. The peel stone comes in, peels it off to the side, and this guy scatters this way. That's basically the idea. So let's calculate the wavelength of the scattered X-ray. Well, one of the formulas I can use off the previous slide here is delta wavelength is equal to h over mc 1 minus cosine theta. Do I have enough information? Let's see. Do I know Planck's constant? Yeah. I just know Planck's constant, right? I actually know two different Planck's constants. I know one in electron volts and one in joules. So it just depends on which one I prefer to use. C, speed of light. I know that one. Angle. Yeah, I was given that 15 degrees. Mass. Well, yeah, let's go back to what I wrote out here. The m is actually the mass of the electron. So good. We actually always know the mass of the electron, right? So this formula is pretty easy to use because you're always going to have Planck's constant. You're always going to have the speed of light. You're always going to know the mass of an electron. So really, all of this right here is always a guarantee. You always have those three variables. So essentially, it means you need one of two things. You either need to know the angle it scatters at, and that'll find you your change in wavelength, or if you know your change in wavelength, you can find the angle it's scattered at. Does that make sense? So, but because I have the angle we're scattered at, we're good to go. Okay, so let's try plugging in some values. Now, Planck's constant can be done in a couple of different ways. Why don't we go with the joules one? Does anyone have that one nearby? It's 6.63, correct? Times 10 to the negative 30, 34. Can I have the units, though? The reason I want that is for the units. Joules times seconds, that's it? Okay. Oh, then we're going to divide this by mass. So that's 9.11 times 10 to the minus 31. I'll go kilograms. And the speed of light is 3 times 10 to the 8. And that'll be meters per second. And then 1 minus the cosine of 15 degrees. Now, only for this example here am I going to deal with the units. You guys can probably skip these units, but I want to just make sure I'm thorough in showing you which ones we're using. The only unit here that's not a base unit is a joule. What is a joule equivalent to? Anybody know? Okay, so it's equal to a newton times a meter. But what's a newton equal to then? Kilograms times meters per second squared times by an extra meter that's sitting there. The reason why I want to do all this is I want to cancel out my units here. This kilograms will cancel that kilograms. This meters can cancel that one. This seconds can cancel one of those ones. This second here can cancel the other one, which means the only unit I have left now is meters. Which is good, because what are we solving for? A wavelength, which is measured in ta-da. Okay, so now you guys can plug this all in your calculator if you like. Now, if this is in meters, I'm expecting a very small answer. Like, I'm not expecting 5 meters, because 5 meters is a radio wave. I'm expecting, like, times 10 to the minus 8, 9, 10, 11, or more. By the way, make sure that you're in degrees, especially for any of you guys that are doing math, and we're in radians. Yeah. Let me know when you guys are going to answer here. Did you get an answer? Let's just solve for the delta wavelength first to make sure we all get this first. You are right, though. We will need to add the original wavelength. What'd you get for the change in wavelength? Everybody else? All right. Sweet. And Rebecca was already ahead of the game here on the next concept here, is that is, though, the change in wavelength. That's not the actual wavelength itself. That's how much it's going to change by. We actually were given the original wavelength, and this is how much it's going to change by. Now, is the wavelength getting longer or shorter? So I need to take this number right here and add the number you just told me. Does that make sense? So one more thing I got to point out here is you got to watch the sig digs for adding, though, because this number right here is really 0.0008266, and then this number right here is 0.00, but like a couple of less zeros. because this one was minus 14, then it's minus 12, and then that's 128. Well, it doesn't stay the same because I think what should happen is the 1 and the 2 are like, this is the minus 12 digit, this is the minus 13 digit, and then this 8, which is this one right here, would actually match up with this one right here. So when you add them to each other, I mean, what did you guys get when you put it in your calculator? Just add them to each other. Did you get 1.36? Yeah. 1.36 times 10 to the minus 14. The point I want to make here, oh, minus 12, yeah, good call. Because this is where the 12 digits is that this 2, the 6, and the 6 here, they really don't get to count when you add them. Do you remember the rules for adding and subtracting sig digs for, for adding and subtracting? Is that you put it at like where you cut it off. And so since this 128 got cut off right here, and then the 8226 was right here, it actually gets cut off right there. So you have to be careful with your sig digs rules sometimes, because it maybe it seems like you didn't add very much to it, but it only added this 8 to that 8 there, bumping up to 136. Anyways, this is now our wavelength 2. The wavelength as this thing exited right here, we now know its wavelength. Is able to follow that? It's a complicated looking formula. It looks intense, but really there's only two variables. You either get the angle or you get the change in wavelength. You're either getting one or the other, and really all the rest of this mess right here doesn't ever change, never. Okay. Second half of the question though, I could ask you for the velocity of the exited electron. This is the one that sucks, because this is now your law of conservation of momentum in 2 dimensions using like what we did in our first unit. So let me try this one more time from the top here. I'm going to draw another picture of our incoming wave, only this time I'm not going to draw it as a wave. I'm just going to use a line just to keep it simpler. And the electron we said was going this way, and the remaining wave was going down this way. And we need to try to find a way to calculate how to pull this guy off. Well, one option we have then, this is option 1. I could break this guy up into a y and an x. I could break this guy up into a y and an x. And I could do a whole bunch of x's and y's and stuff like that from our first unit. You guys remember doing that? Here's another option. I can use the cosine law if I know how. I could say that really this is the original path here. And then why don't I have it so that this is the scattered one that went downwards, and then this is the electron coming upwards. This is my wavelength 2, this is my wavelength 1, and this is my electron. Can you guys visualize that? All of that would need to make a vector triangle for momentum. This is the original wavelength coming in, which is really what I had right here. The wavelength scattered downwards. I picked downwards. It didn't matter which way I picked, up and down. But the wavelength scattered downwards, so I drew that right here. And then the electron itself was going upwards, which is going right here. So far, so good. But here's the other nice thing. That's 15 degrees. Because I do know that angle is 15 degrees, right? Now, I need to not know these wavelengths. I really need to know the momentum here. I need to know the momentum here. And I need to know the momentum here. And if I'm going to use the cosine law, I need to know the momentum of these starting 2 guys right here. But the good news is momentum of waves can now be calculated using the new formula that Compton figured out. Or I don't think actually Compton figured out. I think it was Einstein actually. Where was that formula? Here it is. P equals h over wavelength. So I can calculate those momentums by doing h divided by wavelength and by doing h divided by wavelength and find those momentums. So let's give that a try. Oh boy.